We could get the molar ratio from two different things. What was one thing we could get the molar ratio from? Yep, the balanced chemical equation. And that was, how did we get the molar ratio from that? Yeah, the coefficients in our balanced chemical equation give us the molar ratio, right? Basically, for each reaction that happens, we can have like a one reactant makes three products, for example, right? So that gives us the molar ratio. And what was the other thing we could get our molar ratio from? Subscripts in a chemical formula, right? Subscripts in chemical formula. Right, and that was for if we're looking at, what mass of a specific atom is within a molecule, right? We're going between chemical quantities of single atoms to compounds or molecules. And what was the last thing that we used to convert? What other chemical quantity or number, special number? Avogadro's number, right? And the value of that was 6.022 times 10 to the 23 things per mole. This was just our counting device that defines what a mole is. And we use that to convert between what two things? Moles and number of things. Right, and we just use that because it's a lot easier to deal with a mole that represents a very large number of things instead of dealing with a very large number of things itself. All right, so those were our conversion factors and conversion, bless you, for looking between different chemical quantities. All right, and then the last thing we kind of finished off after you guys took your quiz was looking at things. The two things we looked at were the limiting reactant and the percent yield, right? And what was the limiting reactant? Can anyone give me a short summary or how you would define in words what the limiting reactant is? Yeah, if we have a chemical equation that has multiple reactants, one of those reactants is going to limit how much of the chemical equation can happen. All right, so the limiting reactant was identifying which reactant limits the amount of product we can make. All right, and the general stepwise procedure for that is that first you assume that each reactant is a limiting reactant, and you calculate the theoretical amount of moles of product you can create. All right, once you have both those numbers from each reactant, how do you determine which one is the limiting reactant? Yeah, whichever one makes less product, right? Whichever one makes less product, that's how we determine which one is our limiting reactant. Whichever one makes less moles of the product is our limiting reactant. Right, and so if we're given non-stoichiometric amounts, and that usually just means amounts in grams, because that's actually what we measure when we go through, or when we do chemical reactions in the lab. We don't measure moles directly. We measure grams. So when we're mixing things together, it's not in stoichiometric amounts, meaning we don't have perfect number ratios of molecules in our system. And so we can then calculate what the percent yield of our reaction is, right? And the percent yield told us about what? Who remembers? What was it defined as? Yeah. Yeah, it's the actual yield over the theoretical yield multiplied by 100%. And when you do this, where do you get the actual yield from? Yeah, this is what you measure in your laboratory, right? So when we did the copper lab, where we went through a bunch of chemical reactions with copper, and we see how much metal copper we ended up back with, our actual yield is the mass of copper we measure after the experiment. All right, this is from measurement. And the theoretical yield, where do we get that value from? Yeah, this is from the balanced chemical equation, right? And the amounts that you start off with, right? So if you know how much copper you start off with, and you know all of the balanced chemical equations, that should theoretically tell you, if assuming everything is 100% efficient, what's the maximum amount you can make with two given starting amounts. All right, so that was where we left off our discussion last time. And so now we're going with these ideas of unit conversions and actually using them to calculate useful things for us, right? Where we can actually look in a lab and determine how efficient our chemical reaction was. Why is that interesting? Well, if you ever work in an industrial lab, you're going to be looking at optimizing that percent yield, right? You want to make sure that you're not losing product or reagents to side reactions or somewhere else in the reaction process, because if you lose your reactants, you're losing money, right? So you want to make sure that everything is as efficient as possible. Okay, any questions on what we discussed last time? Maya?
Example 4, the one we ended on.
Example 4, all right, yeah, we can look at example 4, right? So here we have a carbon tetrachloride that's being prepared, right? So carbon tetrachloride is on which side of our reactant, or chemical equations here? It's on the product side, right? This is carbon tetrachloride. We have the tools, we know what that molecule is because we can name those molecules, right? So remember our prefixes and everything. And it's saying how much, this was prepared by reacting 100 grams of chlorine gas with excess carbon disulfide, right? So carbon disulfide and chlorine are our two reactant molecules here. And it's saying if 65 grams was prepared in this reaction, calculate the percent yield. And so here we're not going to have to do a full limiting reactant problem because we're not given non-stoichiometric amounts of each of the reactants here. What information is given to us that simplifies this problem in a way? Like, how do you know you don't have to calculate the theoretical yield from both reactants here? What indicator in the problem tells us that we don't have to worry about one of the reactants? It's the excess part, right? It says excess carbon disulfide, right? So if we have excess carbon disulfide, what does that imply about chlorine gas here? And we can use the terminology of what we discussed last time, so you can use that vocabulary.
Could you ask the question?
If it says excess carbon disulfide, what does that imply about chlorine gas, right? Using the vocabulary, the terminology that we discussed last time. Yeah, it's defined as the limiting reactant then, right? So why? Because, well, we have so much carbon disulfide that we know that chlorine gas is going to limit how much product we make, right? So the fact that it says excess carbon disulfide, that tells us that chlorine gas is our limiting reactant, right? Whenever you see something like this, this tells us CS2 is, chlorine is the limiting reactant. Or in a general, if something is the excess, or if it is presented in excess, it means whatever the other reactant is the limiting one, right? Because you're saying you have so much of this one reactant that you don't care about how much that contributes to how much product you make. It's the other one that's limiting the amount of product you can make from this reaction. So an example of something like this, something else that we've done, is when we looked at our synthesis of magnesium oxide, right? We had the magnesium strips, we put them in the crucible. The magnesium strip is our limiting reactant, right? The other thing we needed was, atmosphere, oxygen gas, right? So why would magnesium be the limiting reactant there and not oxygen? So let's think about a real, something you guys have done. Why would the magnesium strip be the limiting reactant and not the oxygen gas when you're burning it in the crucible?
Because we have less.
We have less, right? We have atmosphere, right? Effectively, we have an infinite amount of oxygen available, right? Air currents and stuff keep putting oxygen into the reaction. But we have a very specific amount of magnesium, right? We can't make more than the magnesium we had with because the magnesium in magnesium oxide comes from that strip. The oxygen comes from the atmosphere, and there's so much more oxygen in the atmosphere compared to the magnesium that was in your crucible. So a way of phrasing that in chemistry vocabulary would say, well, you know, we prepared magnesium oxide with 5 grams of magnesium and excess oxygen gas, right? And that implies that the magnesium is your limiting reactant. So whenever you guys see excess or anything like that, that means whatever else is there is your limiting reactant. And so this one we don't have to look at for limiting reactants to calculate the percent yield. But we still have to calculate the percent yield, right? Which means we need what two values when we're calculating the percent yield? We need the actual yield, right? We need actual yield and theoretical yield. And so how do we get the actual yield? That's the theoretical yield, right? We use the balanced chemical equation to calculate the theoretical yield. How do we get the actual yield? It's given to us, right? That's something that you have to measure, right? So if you're in an exam, I'm not going to have you weigh out a certain amount of product and assume that that's the actual yield, right? You'll always be given the actual yield in a percent yield problem when it's given to you in words like this, right? So this is our actual yield. And how do you know? It says it was prepared in this reaction, right? And it's referring to the carbon tetrachloride that was prepared in this reaction. All right, so this is from the problem. And how do we calculate the theoretical yield then? Yep, we calculate the theoretical yield using the amount of our limiting reactant that we started with, right? Calculate theoretical yield from Cl2 that we started with, right? And what does that involve? And we're going to have to use the molecular weight. That's going to be our unit conversions, right? We're going to have to do a mass-to-mass calculation using our balanced chemical equation. We start off with 100 grams of chlorine gas, and we're going to need to calculate how much carbon tetrachloride do we calculate. There's a lot of C's there. I'm getting mixed up. All right, and so what is the general path, right, that we do? So we're starting from grams of Cl2. What do we have to go to first? Moles, right? We always have to convert to moles first because that lets us go between whole numbers of things, right? So we go to moles, and we go to moles of what? Chlorine gas, right? Because when we go from grams to moles, we can only go between grams and moles of that compound, right? We can't convert between compounds until we get to moles, right? So first we go to moles of chlorine gas using what? The molar mass, right? The molar mass of chlorine gas. And then you go from moles of chlorine to what? What's the next step? Moles of your product, right? Because we need to know how much product we're making here, or what's the theoretical maximum. So then we go to moles of CCl4. And what do you use to do that conversion? The molar ratio, right? That's the balanced chemical equation because that says every 3 chlorine molecules we use, we make how many carbon tetrachlorides? 1, right? So if we have 3 moles of chlorine gas, how many moles of carbon tetrachloride does that make? 1 mole, right? Whenever I say a number of molecules to converting that to another number of another molecule, if I just multiply that by 6.022 times 10 to the 23, now it's just a mole of that molecule, right? So 3 moles now gives us 1 mole of carbon tetrachloride. So we use the molar ratio for that. Molar ratio. And what's the last step then? what do we end with? Grams of CCl4, right? And what do we use to do that? The molar mass. Whenever we're going between mass and moles, we always use the molar mass. And the molar mass of what compound here? CCl4, right? Carbon tetrachloride. Right, so this is a percent yield problem, but baked into it is a mass to mass unit conversion. Right, so first thing we need to identify is what do we need to actually calculate the percent yield? We need the actual yield and the theoretical yield. We identify the actual yield has to be given to us because that's something you measure, which means that to complete the percent yield calculation, we need the theoretical yield. We have to realize that the theoretical yield is the same thing as doing a mass to mass conversion here. And that requires us to identify that chlorine gas is the limiting reactant because we have carbon disulfide in excess. Summer?
I have to get the molecular weight of that chlorine gas, right?
You have to have the molecular weight for chlorine gas, and you have to have the molecular weight for carbon tetrachloride for this problem, right? Molar mass and molecular weight are used interchangeably. Those are the same thing.
And if I wanted to do that, because we have a subscript and a coefficient, should I multiply that 3 and 2?
So can anyone else answer that question? When you're calculating the molar mass of chlorine gas here, do you use the coefficient at all? If we're calculating the molar mass of chlorine gas right here, right, so in this first step, do we use this coefficient at all in calculating the molar mass?
I'm guessing no.
Yeah, we don't use the coefficient, right? Yeah, of course not, right? So we don't use the coefficient. Why? Because our molar mass is in units of what?
Grams per mole.
Right, yeah, so the molar mass, the units of the molar mass is grams per mole. It's not grams per 3 moles. It's not grams per 2 moles, it's grams per 1 mole, right? So we don't use that coefficient until we get to the molar ratio.
Okay.
Technically, you can bunch it all into one calculation like that, but that's gonna make things messy and I think a little bit hard to understand. The coefficients, we just use for our molar ratios.
Thank you.
That's a good question. All right, so why don't you guys spend a couple minutes going through this calculation here, right? So actually do the work for step 2 here and see if you can calculate the percent yield. Equation for percent yield here. Percent yield equals actual over theoretical times 100. Let's start going over this. Okay, so the first step was to start with the number of grams. We start with 100 grams of chlorine gas, right? 100 grams of chlorine gas. I always write the molecule or compound that we're looking at after the unit because we're going between chemical quantities of different compounds, right? So we want to make sure we know what we're talking about. We're talking about the limiting reactant here. And so we use the molar mass. What's the molar mass of chlorine gas? 70.906, you said? 91 will do. Grams of chlorine gas per 1 mole of chlorine gas. That was our first step. What's the next conversion? The molar ratio. And what is the molar ratio for this reaction? 1 to 3 carbon tetrachloride to 3 chlorine gas, right? So what should be in the denominator and what should be in the numerator? What's in the denominator? 3 moles of Cl2. I get that from the balanced chemical equation here, right? This is where I get the 3 from, per 1 mole CCl4. Right, so now units of grams of chlorine gas cancel out and moles of chlorine cancel out. In the last conversion is what? Between what two things?
Grams of
Yep.
CCl4.
Yeah, to grams of CCl4 from moles of CCl4. And so how do I do that? What do I use?
153.80.
53.80 grams CCl4 over 1 mole CCl4. Right? Because we want grams in the numerator because we want to end with units of grams, right? So moles cancel out, and we're left with grams. And when you plug this all in, what do you guys get? Like 80 to 90 something. 72.298. 72 point, we'll just do 230. We'll just do 0.3. 72.3 grams of CCl4, right? Yeah, so CCl4, the molar mass. Who else can answer? How do we get the molar mass for CCl4? What values are we getting, and where are we getting them from, and then what do we have to do with them? Where are we going to get the values that we need to calculate the molar mass of CCl4? From the periodic table, right? Which is the atomic mass of each of the elements that are in our chemical formula. And so we have 1 carbon atom and 4 chlorine atoms. So when we're calculating the molar mass, what do we have to do? Yeah, so we have to make sure that we get the number right because we have 1 carbon. So we have, what is it, 12.01 grams per mole plus 4 times the molar mass of each chlorine there, which is what, 35.45?
Yes.
35.45 grams per mole. This number here comes from the subscript in the molecular formula, or the chemical formula, right? And when you plug this all in, you get 153.80 grams CCl4 per 1 mole CCl4. Right, so that's a good question, good review, because this you want to be very comfortable with, right? This should be, okay, I see the molar mass, I can look at any chemical formula and figure it out, even if it's, something really annoying like what you had on the quiz where you had 13 of one element, 18 of another, and 5 of another, right? The idea is the same for every molar mass you calculate for any molecule. All right, any other questions on anything we got in this unit conversion pathway here? Okay, so now we have 72.3 grams of CCl4. This was what value in our percent yield calculation? This is the theoretical yield. And how can we kind of like keep an idea if we're on the right track or not, right? What about this number tells you that this is okay and I'm not doing anything wrong right now compared to, right? If we look at the actual yield versus our theoretical yield, what can we say about those two numbers?
Well, the actual is smaller.
Yeah, the actual is smaller, right? The theoretical yield is more, which makes sense because theoretical is assuming that every single reaction that happens is 100% efficient, right? It's theoretically the maximum we could make, right? So if our theoretical yield was less than our actual yield, we would say, okay, there's probably something's not right here, right? So as long as our theoretical yield is more or equal to, at the very maximum, assuming the reaction is efficient, then we're good, right? So this is greater than actual yield. So that tells us we're on the right track here, right? And then if we calculate the percent yield, what do we plug into our equation? It's actual over theoretical times 100. So we have 65.0 grams CCl4 over 72.3 grams CCl4 times 100. And what percent did you guys get when you did that?
89.90.
0.9%. Vanessa? I'll tell you if you have to worry about significant figures. In this problem, the only thing that would give you a significant figure would be the two numbers that were given for you, so it would be 3 sig figs in the final answer. As long as you had 3, that would be appropriate. Because we've already talked a lot about sig figs and stuff. If I say make sure you include significant figures, you just have to make sure that, well, we have 4 in one and then 3 in the other, so limiting would be the 3 for a final answer. But it would be a very small percentage of a problem at this point. Like, mostly insignificant. Because I don't want you guys focusing as much on that as on the ideas of these unit conversions. Right, and what is the mole and how are we using it? All right. Yeah, I'll go back. Mm-hmm. And then Summer, you can ask your question.
When we get our percent yield, just the percent is fine, right? We don't need like a unit or anything attached.
Yeah,
to
so
it?
percents are unitless numbers.
Okay.
And the reason a percent is a unitless number is because whenever you're calculating a percent, whatever's in the numerator and the denominator has to be the same units.
Okay. Thank you.
Mm-hmm. Right, and so pretty much most of the things we do from here on out, aside from maybe some things with acids and bases, are just gonna be variations of things like this, right? Keeping track of units. If we talk about ideal gas laws, instead of looking at mass to mass calculations, you can do mass to pressures, mass to moles. You can use that for solutions and everything, right? So this idea, the idea of counting things and how you can count different things kind of stays with you in chemistry for the remainder of the subject. It stays with you in chemistry for the remainder of the subject, right? So yeah, fancy way of counting things is chemistry in a nutshell, right? Because how do you deal with stuff that has very, very large numbers, right? Right now we're counting things explicitly with the idea of the mole. If you go far enough, you'll start using tools like statistics to analyze chemistry, right? Yeah, so we're not going to do that, so you don't have to worry about that. But if you like statistics, right, you can start to think of chemistry in the same way. How do things behave statistically rather than individually? Okay, any other questions on this one? All right, so briefly we're just going to talk about using energies, right, for different chemical reactions, right? So energy in chemical reactions, we've talked a little bit about how when reactions happen, they can release or absorb energies the same way changes of state can, right? So when we go from ice to liquid water, for example, the molecules take in energy from their surroundings because they have more energy, right? When we evaporate, gas molecules move a lot faster than water molecules, so they have more energy, right? In chemical reactions, we have the same thing, except we're not looking at just the movement in terms of the energy, but actually the energy that's stored in the chemical bonds, right? So products in reactants have different energies because they have different bonds usually, right? And when we're making or when we're doing chemical reactions, we're breaking and forming bonds. So the energies of things will tend to shift. And when a chemical reaction happens, the energy of the products and the energy of the reactants gives us either the amount of energy absorbed, the difference between them, the energy absorbed from the reaction, or the energy released by that reaction. And so if we have a plot like this, right, so this x-axis is called the progress of the reaction. Another way of, you might see that, is called the reaction coordinate. It's basically saying as whatever it means to go from products to reactants. And there's different ways we can think of that. But progress of reaction or reaction coordinate means going from reactants to products. As we go along the x-axis, we're moving towards the products. And the y-axis here is energy, right? So what are the units of the y-axis generally going to be? Joules can be one, or we could use calories or something, right? It's energy. And in this reaction, the reactants start at some value, right? We don't know what that value is. The absolute value doesn't really matter in actuality for what we're looking at. But that's the energy of the reactants, meaning all the energy that the electrons have when they're in these orbitals around the atoms and in the covalent bonds between them or the ionic bonds between the compounds. As the reaction proceeds, we usually need to add a little bit of energy, which is called the activation energy, to the system to get the reaction to happen. All right, so does anyone have any idea of how we add energy when we want reactions to happen in the lab? You can have a catalyst, though a catalyst is going to reduce the activation energy, right? So a catalyst will reduce the activation energy, which means we don't have to add as much energy. But what are some ways that we add energy when we're in the lab? Can anyone think of anything? Heat, right? With the crucible, we heated up the reaction to make magnesium oxide. Does anyone think of anything else? An even easier way. You don't have to use any chemicals to do it. If you want to get your sugar to dissolve in coffee, what do? You stir it, right? So stirring is another way of adding energy to a system, right? You're adding kinetic energy to the molecules, that adds energy. So that little bit of energy that you add beforehand is called the activation energy. Then you move to the products, and the products have some other energy that's associated with them, right? So this is the energy of the products, and this is the energy of the reactants. And the difference in energy between the products and the reactants, right? If we wanted to look at the change in energy, which in chemistry, what this is called the enthalpy, right? Which is designated by the variable H. That's just the difference in energy of the reactants and the products in this case. And if we have a delta E here, what does that usually mean? Change. And how do we express that mathematically in terms of two values? The final minus the initial, right? So this is something like E final minus E initial, which in this case is the product minus the reactants, right? So this is equal to the energy of the products minus the energy of the reactants. And so there's two things we pay attention here. The value of this change, right? That tells us how much energy we're talking about, and the sign of this change, right? So in this case, is the energy of the products higher or lower than the reactants? It's lower, right? Which means that we've lost energy somewhere. What that means is that we've released it to the surroundings, right? So this is what we call an exothermic reaction. And what this means is delta H is less than 0. It's a negative value, right? Because if this number is smaller than that number, that gives us a negative answer, right? So this is a release of energy in this case.
So we do or we don't want a negative answer?
It's not whether you do or you do, or you. It's not whether or not you want it or not. It just is what it is, right? It's just the way the universe works. Some reactions are exothermic and some are endothermic, right? For example, when you want to cool down and you have water on your skin, the evaporation of water is endothermic, so it takes in energy, right? Which means it takes energy from your body, takes temperature away, so that you can cool off. If you want to design dynamite to blow up mines, right, you want something that releases a lot of energy. So you want a very exothermic reaction. All right, so if we have a specific reaction, so am I good to go on to the next slide? Vanessa?
So the bluish, greenish line in the thing, that kind of shows like how the energy.
Yeah, so that's like as the reaction is happening, what's the energy of everything that you're looking at? The actual, what that means can be very complicated for a lot of different systems, right? Because this means molecules are slowly breaking bonds, forming bonds. So you probably have, this state right here. You guys don't have to know this. It's called the transition state. And it's probably some arrangement of the atoms that's halfway in between the products and the reactants. So if you looked at the specific molecules of that reaction, and it's saying how is the energy of the system, meaning all the reactants and the products, changing as we go from reactants to products. So you have to increase the energy. The transition state is probably not very happy, which is why, if you're at the top of a hill, you put a ball at the very top of a hill, it's going to roll down either side, right? The transition state is that unstable state, and it's either going to move to the products, or it's going to go back to the reactants. But yeah, it's a deep concept to think about, right? That what does it mean for the energy to be moving as we move from reactants to products? And a question a lot of people still think about today is, well, how do you define that, right? And that's why they say reaction coordinate, because maybe it's the distance between two atoms you're looking at. But if you have molecules that have hundreds of atoms, it's all of a sudden not just a distance between two molecules. How do you define a collective coordinate for the reaction to happen? But yeah, it's something a lot of people still think about in, state-of-the-art studies right now.
So exothermic is the release and endo is absorbed?
Yeah, so exothermic, right, is going to be the release of energy. So if we have this reaction here, it proceeds and there's some energy value associated with it. If it is an exothermic reaction, that means we're going to be releasing energy. So as this reaction happens, we convert hydrogen gas and nitrogen gas to ammonia. You would feel heat if it was in a test tube, right? The test tube would get warm. And another way of thinking that is that energy is one of the byproducts of the reaction, right? So we can think of this as a byproduct of the reaction. And a byproduct is just a product, so that's why you can say it's on the product side of this reaction. And the reason we can think of that is because it can make our stoichiometry calculations a little bit easier, right? So to kind of, get you guys thinking, that means that if we start off with 3 moles of hydrogen gas, we produce 22 kcals of energy, right? We release this much energy because it's like a product in this reaction, right? The coefficient for this quantity is 1, and this is just another product in this reaction. The sign of this just tells us if it's exothermic or endothermic, right? So when the sign is negative, that means that it's exothermic. If we were to look at another reaction, here we see that the energy of the reactants is lower than the energy of the products, which means that delta H is equal to the energy of the products minus the energy of the reactants. This is going to be greater than 0 now, right? Because the products has a larger number than the reactants. And so that's like saying we require a little bit of energy for the reaction to happen, meaning that it's like a reactant in our reaction. We need energy for this reaction to move forward. Right? We have to put some energy in and keep that energy in the reaction to actually make these products. Which means that if we produced 1 mole of oxygen, we had to take in 137 kcals of energy. And this reaction is called endothermic. So this is an endothermic reaction. We take in energy from our surroundings. And this is like when water evaporates on your skin, it cools you off, which is how sweat works. Okay, any questions about the definitions?
Can I see the previous one?
Yeah. All right. So that means that we can use stoichiometry the same way we have with our mass-to-mass calculation, right? Because for every coefficient in our chemical reaction, so this is our endothermic reaction, that means that if we started with 2 moles of water, that would give us 137 kcals of energy. If we produced 2 moles of hydrogen, then that means that we required 137 kcals of energy for that reaction to happen. And if we produced 1 mole of oxygen, we produced 137 kcal of energy, right? When we have it is a reactant, right? So this is like plus 137 kcal in our reaction. It's kind of an unfamiliar way to look at a reaction, but it's to emphasize that our molar ratios that we usually use to go between different compounds can also be thought of when we're looking at energies of the reaction itself too, right? For every 137 kcals, we require 2 moles of H2O. For every 137 kcals, we produce 2 moles of hydrogen gas, right? So the idea when we're looking at these reactions is first identify is it exo or endothermic. That'll tell you what side of the reaction to put the energy value on. And then that gives you a conversion between moles of that compound in energy required or released during the reaction. Which means that if we can go from moles to energy, we could probably also go from grams to energy, right? If we were to add one extra step, going from grams to kcal, what would we have to do first? Let's say we said we had 10 grams of water.
The mole again?
We would need to convert that into the number of moles of water. Of H2O. And then we could use the moles of water using one of these ratios here to get the value of energy that was required for this reaction. Right, so it's the exact same type of calculation we're doing before, except the first step here would be just using, how do we go from grams of water to 8 moles of water? We use the molar mass, right? That's the same as before. We use the molar mass to always go between grams and moles. And then what would we use to go from moles of water to energy absorbed for this reaction? It would be this ratio right here, right? This gives us the ratio of the moles of H2O to the energy per reaction. All right, so you'd use this ratio right there. So really, like I said, we're still doing the exact same type of calculations we did before, except now we're just adding energy into the equation, right? Because for an exo versus an endothermic reaction, energy is like a reactant or a product in these reactions because it's either released or absorbed, the same way a product is released from a chemical reaction or a reactant is absorbed in a chemical reaction.
So that could also be joules over moles.
Yeah, so for example, if I ask the reverse question, I put, 10,000 joules of energy into this reaction, how many moles of water would I consume? Or how many grams of water would I consume? It would just be going in the opposite direction. Right? In chemistry, if we go in one direction, it's a good idea to be able to go in the opposite direction. Okay. So if we're given a reaction like this, the exothermic reaction of the release of energy from making ammonia, how much heat in kilojoules is released when 50 grams of ammonia form? Right, so let's first come up with a path from grams of ammonia to what? What's our final unit going to be here? It'll be kilojoules, right? It'll be units of energy, right? So we're going to go from grams of ammonia to kilojoules for the reaction. And how do we go between those? What's the first step going to be? Grams to moles, right? Because we always are going into moles when we're looking at counting things, right? So moles of what? Ammonia. And then we use what to do that? The molar mass, right? Whenever we're going between mass and moles, we use the molar mass. And then from moles of ammonia to kilojoules, How are we gonna do that? It's gonna be a molar ratio involving the energy, right? Molar ratio. Delta H here. The sign of delta H tells us that this is a exothermic reaction. But when we make the molar ratio, we don't have to use the negative sign there because it's asking how much is released. The negative sign and saying how much is released is the same thing, right? So just to keep our numbers positive, we're gonna keep everything positive. So if we start from 50 grams of NH3, we use the molar mass. What's gonna go in the denominator? Whatever the number is, right? So nitrogen is 14 point what? I can't see. 14.17 plus, right, the molar mass, NH3, 14.73, 14 point what? 14.01, okay, that makes it easier. The molar, okay, all right. Grams per mole. Oh, you already finished calculating the molar mass? So that's the total molar mass for ammonia? 14.01, or is that just for nitrogen?
That was just for nitrogen.
Okay, okay, all right. Plus 3 times 1.01 grams per mole for hydrogen, right? Because each ammonia molecule has 3 hydrogen atoms. That's where that comes from. Which should give us 17.04 grams of ammonia per 1 mole of ammonia. And what's the conversion factor for the next one gonna be?
Mole to mole.
Right? So normally when we're going from reactants to products, we use mole to mole, right? Except now we're going between moles and energy directly. Yeah, it's the conversion between them. So what is our conversion for this? For every how many moles of ammonia, we release how much energy?
2 moles for 92.
NH3 equals 92.2 kilojoules released, right? That gives us 2 conversion factors, 2 mole NH3 per 92.2 kilojoules and 92.2 kilojoules per 2 moles of NH3.
The second.
Yeah, we use the second one. How do you know you use the second one?
Cancel out.
Yeah, the units of moles are going to cancel out, which is what we want because we want units of kilojoules in the end. So we get 2 moles NH3 per 92.2 kilojoules. Moles cancels out, grams cancel out, and we're just left with units of energy, which is what we want. So if we plug this in, we get 50 times 92.2 divided by 17.04 divided by 2 is 164.2. We only have 3 sig figs, so just 164 kilojoules are released when we have 50 grams of ammonia forming. Sam?
Is there a formula for moles to kilojoules?
There's no formula for moles to kilojoules. We get it from our stoichiometry, right? So if the reaction is exo or endothermic, that tells us what side of the equation that energy would go on, right? So if it's endothermic like this, that means we require energy, so it's like a reactant. If it's exothermic, it's like a product. That means that every time this reaction happens, if we use 2 moles of H2O, we require 137 kilojoules. If we produced 2 moles of hydrogen gas, we required 137 kilojoules. So that's where we got that ratio from. So the tricky part here is actually identifying, the language. Are we releasing or absorbing energy? Because we want to keep our energy values positive. Tiffany? What'd you get? 135? Let me see, did I miss a decimal place? 50, 92, 4, oh, I put, 14, so yeah, you're right. 135. Thank you for correcting me. Yeah, I put 14.04 for some reason. 135 though, right? Just keeping you guys on your toes. All right, so now it's the exact same thing, right? The tricky part of these is just identifying in the phrasing of the question, which direction are we going in, and is it a reactant or is it a product? In terms of this question, it doesn't really matter, right? Because if it's exothermic or endothermic, it just meant that we released energy. In general, your answer should be positive, and the ratio is always going to be positive because of that. Summer?
Oh, I was just thinking.
Oh, okay. Vanessa?
Are you ever gonna make us identify like which one's exothermic, which one's endothermic?
The only way I would ever ask you that is if I gave you everything that's given right here, and I said, is this exothermic or endothermic? And you would say, well, because that's negative, that means it has to be exothermic.
Okay.
You would never know beforehand if it's exothermic or endothermic. Or, in a conceptual question, you say, okay, this reaction happens in your test tube and it gets hot. Is it endothermic or is it exothermic? Right? It released energy, so it's exothermic. The test tube gets cold, it absorbed energy, that means that it's endothermic.
And you write them on separate sides, depending? Like the.
Yeah, you can write it on separate sides of the equation, right? If it's exothermic, that means we release it, it's like a product in our reaction. If it's endothermic, we required it, which makes it like a reactant. In terms of the molar ratios for the energy, it doesn't really affect anything, right? Because it's the same ratio, that energy per whatever mole you have in the problem, right? Like if that was on the product side here, these ratios would still be the same if that's on the reaction or the product side. But conceptually, that's just how we build the chemical reaction if energy is involved, or when energy is involved. Actually doing the mechanics of the problem, it doesn't really change how you deal with it. All right. Okay, so any questions on that? No? All right, so there's another example. We can probably review that one on Monday. We're going to jump ship over to solutions real quick because it's related to what the lab is. So for the last 15 minutes of lecture, so we're going to talk about solutions. But if you want to think about this over the weekend, and we'll go over it together on Monday is what we'll start off with. All right?